Telecompaney Douglas Productions and Svetlana Productions. Movie Winding Coils from Microwave Oven Transformers Wire. Sponsor of program Douglas Konzen. Director of stage Svetlana Konzen. Inventions of Douglas Konzen. Enjoy the movie and write what you think.
Okay, I've wound up yesterday a total of 4 coils that slip on the 3-phase transformer core, and I used microwave oven transformer wire because I didn't want to buy a big old spool of 20 gauge wire for $200 or whatever it costs these days. And I have a lot of these transformers to hack into. So here's a microwave oven transformer right here. What you do is you just get a metal cutting saw and that seam right there that's a welding seam, just cut it. Everybody probably knows this already. So now you cut this off. And then you pull this out. And then you use this wire to wind your coils. Notice there's a bunch of crap in here between the primary and secondary. There's some steel laminates. Take those out. There's this red wire, which is some sort of wire that goes to the microwave itself system. Not sure what that's for, but there's a big red wire in there. Take all that out so that you're going to have this. And if you want to make an improvement of microwave oven transformers, now do your own windings all around this space here. So you can get these for free, all these microwave oven transformers, and they have a lot of good wire. Sometimes it's aluminum, but sometimes not. I have this thing. I took it out of a treadmill, I think. I really don't know where I got it from, but it's a choke, and it's got a lot of nice wire. Now, I did a lot of winding already, and I wound up these coils here that came out really nice, but it's very thin wire. So like this one is 89 ohms impedance, this one's 676, and this one is a ridiculous 678 ohms. And this didn't really work well with these transformers we're building, you know, because there's just no real current to be slamming around forward and backwards inside these cores. I think you'd have to have about 600 volts to get these to have, you know, to be doing something. I made these two, and these are also ridiculous ohms, 422, 413, 377. But they're nice little coils. Maybe I'll use them for something else someday, or I'll run this at very high voltage. But I don't really want to do that. I'd rather stick around 120 volts. So this choke, you just gotta unbolt it, these bars, and it should come right apart. But that's another thing. Okay, let me show you my rig to wind. And I have kind of a different way to do this. Okay, that's basic. And here's the coil, and I have this piece of wood in here, and it slides right out. And I put these shims on each side to so I could adjust exactly the width. And I would make some, and they were too big and it'd be too much slop here, so I take some shims out here. Anyways, this is what's inside. I tried these made out of foam, but you don't want that because it compresses and it doesn't come out very good, the final thing. So here's the trick I do. You saw how easily that popped out. Now inside here is a sheet of Teflon. It's white Teflon. I bought this online. I think it's the only place you're going to be able to get Teflon. It's about this thick. I was making guitar picks out of this, but this was too thin. I got some thicker stuff. And Teflon melts at a very high temperature. I think 460 degrees or something. So also when I do a wind, after each layer, I wrap a layer of Teflon plumbing tape around it, you know. Common stuff. And I think this will help cool it down. It might be you don't want black tape on the final outer coating. You'd want paper just in case things get hot. The black tape won't hold the heat in, but I don't think it's going to matter. So now let me pull this out. See that? That's that Teflon. You have a break at one end, and you just hold it together with some masking tape. See, it comes out easy. And at the break there, I just have some masking tape to hold it together. So there it is. That's what goes inside here. Just like that with the top on it. So now you can wind it with a drill. You know, a drill stuck here. Wind it up with a drill, which I did with this thin wire. It was kind of fun. Just whipping these coils out with an electric drill. But for this thicker wire, I just did it by hand because it just wasn't working very well with a drill. And it didn't take very long. So I've seen in my microwave oven transformers a thinner gauge wire and a thicker gauge wire. Here, this is more So I did these with a thick wire. It's pretty thick. I'd say I can't say what gauge. I'd say 12 gauge, maybe only 14 gauge or something. But it's just whatever you get out of your microwave oven transformer. So there's what I'll be getting from this one. Now, what I've done is I've wound like this coil out of this gauge wire, and then I made another one of the same length of wire, which is 45 feet 6 inches. 45 feet 6 inches of wire in this thing, okay, and 45 6 inches of wire in this thing. But this one's wound like this, this one's wound like this, and I did the same. I made a thick wire one. I have two thick wire ones that are of opposite winding. I don't know why, but it seems like it's better to have this of opposite wind. Doesn't seem like it would make any difference. You just have a different, either put it in down here or down up here to change the directions, but it might have a big difference. So anyways, so what's nice is when you make coils like this, you can experiment with them like this, and then pop one of these thicker winds in and see what happens. What I want to do is have this one use up all the wire, have this one big, have it maybe twice the length of wire in these two, and there seems to be some space left for me to wind a lot more wire. Now the thick wire, this is 37.5 feet, and interesting, when you have a microwave oven transformer, if it's this thick wire on the low impedance side, it's about 75 feet, what I found. And if you have the thinner wire, like this, looks like it's the thinner wire, it's still thick wire, but it's not as thick as the other. And it was 100 feet, about 100 feet. And so I expect this is going to be about 100 feet of wire coming out of here. So that's good to know. The reason I have 37.5 feet is because the thick wire coil was 75 feet. So I split it in two so I could make two coils from one microwave oven transformer coil. And same reason for the 45 feet 6 inches is it's about 100 feet, but I wasted some of it, so it came out to be 45 feet 6 inches for the thinner wire coils. That's this wire. So now remember how it works is this coil is shorted out. It creates kind of a null, N-U-L-L, magnetism in the core here. And this coil has the load across it and a fairly large capacitor, maybe 42 UF, high voltage oil filled capacitor. And if you put if you put a large capacitor across the coil, which is the load, also going to the load, and I happen to have a light bulb, what happens is it shoves the phase shift. Normally the voltage comes first, followed by the current, but when you do that, capacitive leading, when you put a large capacitor across the load from the secondary, it initiates ferrule resonance. It makes the core go crazy, and the core is resonating. It might not be absolute ferrule resonance, but it really excites the core. And when that core is going back and forth in AC, that's what induces power, AC power, into the windings around it. Okay, so that's how it works. And this is the primary that takes in the AC power from the grid or from an inverter. And it would be nice if this is of higher impedance, because then you're going to have lower draw. And the action is happening between from the reaction of the load and the capacitor I saw on the scope, it was 90 degrees phase shift, capacitive leading. And what happens here affects what happens here. And I saw a 90-degree phase shift on the input, which means that actually there's no real watts going in. It's all reactive power going in. So it's a strange one. And I've explained this before, but I don't know if anybody gets it. But if this is, let's say you put AC power in here, and now just look at the first half wave of the sine wave. If this is north and this is south, and what we're dealing with is the back EMF. It's actually the back EMF running through. It's a magnetic force, so the back EMF is running through the core. It's not flyback, it's a magnetic force. A back EMF is running through the core over here, and that is what is inducing power in these winds here. Okay, but how do you get the back EMF to make the choice to go all the way over here and run through this coil? It's by shorting the coil here, because normally if this was north and south, the back EMF is going to be south going this way, south going this way, because it's an opposite magnetic force. So if the magnetic force this way is north, back EMF is going to be south. Okay? And so it's eventually going to be a south magnetic force that enters this at the top. And it should be a north magnetic force that exits at the bottom. But this one, this coil and core leg is in between this and this. Okay? Now, go back to, let's just say this has north and south. That means that north, south, and then this would be north. I'm talking about forward current now. This is north and this is south, and it's just regular normal current. It's going to go over here. It's going to be north, south, and this is going to be north. It's going to attract the south into itself. and then it's going to come out south. And remember, this was north on the top, so it's north, south, north, south. Okay? Now, if this is south and the back EMF is south, it's going to like say, no, you can't go this way. You can't go this way and get over here. But if this is shorted out coil, it's going to allow this south magnetism to go over here. And this is now, it's the back EMF doing work in this far coil, the C coil. Isn't that interesting? Hector calls it a reverse induction magnetic amplifier. You're making that back EMF do something besides just go back and restrict current flow and raise the draw and everything that back EMF does. Well, have it go over here and induce power into these coils over here. Why not? And I believe the polarity is going to suck it right back in. So you got a loop of back EMF that induces power over here, and it reinforces, it recycles and reinforces power of the primary too, because it's entering of the right polarity. Because if you try to shove the back EMF in a bucking field, it's not going to want to go that way. Okay, so that's how I think this works. I might be completely wrong, but I don't think so. But maybe I am. So there we go. So that's it. Now, I want to have these ones of low impedance and really making some serious current. And remember, if this whole core is in ferro resonance, it's going to, if this is of low impedance, it's going to really be making some serious power over here. So what I want to do next is take out these windings and or these windings and wind another coil here of not 45 feet, but about 90 feet, 85, 75. Have a lot more winds over here so the impedance is lower, so the power draw is less. And then have these, the thick winds, that is causing this reverse magnetic field induction in this coil. So I guess that's about it. Can't think of anything else to say. Okay.
Thank you for watching, guys. Thank you. Thank you very much.